Alright, guys, this is Chapter 8, Problem 36, otherwise known as the infamous ice problem, and this is the solution. So, first, you should probably draw a diagram of the problem. There's a boy sitting on the top of an ice mound here, and then he's going to slide a certain distance, and then when he reaches a particular height, he's going to no longer be in contact with the ice. And the problem asks you, at what point does he, at what height actually, does he lose contact with the hemisphere of ice? So the first thing you'll notice, I drew it here, is that at some particular arc length, the arc length doesn't really matter, so I'm not even going to give it a variable. He's going to fall off the ice, and that'll be related to the actual height. The arc length will have obviously an angle associated with it, and then using a neat little trick of geometry, you'll realize that this angle is actually the same as the angle between the radius here, this radius, and the height he comes off. And down here I drew a triangle to make it easier to visualize. And thanks to trigonometry, we can find this relationship here, that the height is equivalent to the radius times the cosine of the angle. All right, well, that's the first part of that little problem right there. Hold up while I attempt to fix this again. So the next step would be to draw free body diagrams. I drew two of them. One with the boy at the top of the ice mound, and then another at the actual point where he comes off. And the thing you'll notice is that all of these thetas that I keep drawing and all of these angles are the same angle. So the angle between the normal force and the vertical, or between the line parallel with the normal force and the gravity, is the same as the angle between the radius and the height. So we'll draw the centripetal summation of forces here, summation of centripetal force, because this is also not only a potential energy problem, but also a rotation problem. So centripetal force here is equal to negative mass times v tangential squared over the radius, and it is also equal to the normal force minus the force of gravity times the cosine of the angle. Now we're gonna do a little bit of trickery here that you may or may not consider valid, but you're gonna assume that at the point that the boy actually comes off the ice mound, the normal force is equal to 0 here. So then we just do some algebra and we solve for v squared. And at this point, you're probably wondering why there's no actual energy involved. Well, here it is. We have the negative change in potential energy equivalent to the change in kinetic energy. And if you're wondering why it's radius minus h, that's because I distributed the negative. It would have actually been h minus r, final minus initial. But since I distributed negative, it's r minus h. And then a whole bunch of algebra comes in, and we solve for v squared. Now, we're going to equate that v squared we have up here with the v squared we have down here. And you're going to get that expression, and the g's cancel. And you're going to come down here, and you're going to notice that I substituted h for r times the cosine of theta. And you come back here, and you'll see that I did that there. And we just do some algebra, and we solve for the actual cosine of theta, which is 2/3. And now the problem is as simple as substituting cosine for cosine of theta. So r times the cosine of theta is equal to 2/3 r, and 2/3 of 13.8, which was the given length for the radius, is 9.2 meters, and that's the height that the boy comes off.